Humanity's future is in space. If we truly desire it, interstellar travel could become possible within our lifetime. But what does it take to build a spaceship? Why don't we see traces of vast empires in our galaxy? As Elon Musk has also pointed out, is our galaxy filled with the ruins of single-planet civilizations? Is colonizing other star systems really that difficult? Recently, some interesting ideas about space travel technologies have been discussed. We're talking about momentum-violating M drives, the wormholes from Interstellar, and the Alcubierre warp drive. The last one is quite exciting, and yes, we'll get to that. However, I must point out that humanity's first journey to the stars should not depend on distant technologies. And it must not. Our first starship will be built with technology that already exists. I'm optimistic, but we have to be realistic. Now, building a spaceship will require enormous political cooperation, financing, and focused effort. My God, it's so massive that we'll have to assemble it in space. So let us assume humanity's future is at risk, and we've discovered a new Earth in the Alpha Centauri system. It's only 4.4 light years away, but first we need to reach Kugelblitz and the approaching K1 asteroid. Therefore, we must focus on a single design and concentrate on our best opportunity. What are we going to build? The key point here is finding the right balance between the speed of the spacecraft and the time required to develop the technology to build it. If the ship we launch in 50 years will be surpassed, then launching a slower ship within 20 years doesn't make much sense. This balance relates to something called the weighting calculation, and we want to get it right. First, our first option, classic rocket fuel. This looks difficult, but for example, the fastest crewed vehicle so far was the Apollo 10 rocket, reaching about 25,000 miles per hour. That means reaching Alpha Centauri would take roughly 120,000 years. No. The biggest limiting factor in space is fuel. Conservation of momentum is a huge obstacle. If you want to learn more, there's some serious rocket science in this section. The rocket equation shows that maximum velocity depends on exhaust velocity, fuel mass, and spacecraft mass. If you want to reach Alpha Centauri within a human lifetime, you need to achieve 10% of the speed of light. But to do that with any liquid rocket fuel, you would need a fuel tank larger than the observable universe. Not efficient. But there are two ways to reach high speeds. Push a lot of mass backward, or push less mass at much higher speeds. So yes, let's choose the second option. We only want the fuel with the highest possible energy density. Therefore, converting rest mass directly into energy seems like the most logical solution. Remember, E equals mc2. The Sun does this quite well, so let S build a motor that works like a mini-star. Second option, fusion technology. In fact, why not choose a middle ground and use nuclear bombs detonated behind our spacecraft to benefit from the explosions? This was a real option considered in the late 1950s and 1960s by Freeman Dyson and others for Project Orion. Let us think about our modern thermonuclear weapons and launch a spacecraft whose mass consists of roughly 1/3 300,000 1-megaton hydrogen bombs, detonating them over a month to accelerate at 1 g up to 10% of light speed. Great. If we assume we don't have to slow down at the other end, we'd reach Alpha Centauri in 44 years. But actually, let's not forget that slowing down is a major problem. We'd have to spend half our fuel on deceleration, cutting our speed in half. So for a one-way trip, let's make that 90 years. That means we need to carry 3 generations of humans aboard and pray that babies born in space are healthy. Still, maybe this technology is the most achievable one. We already know how to build bombs. Long live the Cold War, live. Although the 1963 Nuclear Test Ban Treaty prohibits nuclear weapons in space, maybe we could make an exception for the future of humanity. There are also quite impressive alternative methods. Controlled thermonuclear reactions on board, fusion rockets, explosive concepts like Project Daedalus, or ongoing fusion research. This way, exceeding 0.1 light speed might be possible, though probably not much faster. It's a great option and truly feasible, but controlled fusion technology is still under development and faces many challenges. Rocket science and nuclear physics, as you can imagine, are tough fields. However, fusion converts less than 1% of rest mass into energy. What if we could approach 100%? That's where the third option comes in: antimatter propulsion systems. When matter meets antimatter, it annihilates, releasing most of the rest mass as energy. This is an extremely effective fuel. For example, about 10 grams of antimatter would be enough to get us to Mars in a month. The biggest challenge is that collecting and storing antimatter is incredibly difficult. We can produce it in particle accelerators, but the process is slow and extremely expensive. We've only managed very small numbers of antiprotons, not the kilograms needed to reach the stars. If we could hypothetically increase antiproton production by 100 trillion times, then pion rockets might become possible. When a proton and antiproton annihilate, they produce charged pions traveling near light speed. Guided by magnetic fields, these pions provide thrust. This means roughly 50 times more energy per kilogram compared to the best fusion alternatives. With low fuel weight, our maximum speed would only be limited by how much antimatter we can produce. 0.5 C is possible, meaning Alpha Centauri could be reached in just 9 years. Even 0.8 C might be achievable, which would be amazing because time dilation would reduce the perceived travel time for astronauts to about 3.3 years. Okay, rockets are great, but what if we didn't have to carry fuel at all? What if we could sail to the stars on a wind made of light, with light sails? We'd be talking about a 1-kilometer wide sapphire-coated sail driven by a massive space laser emitting energy equivalent to 100 nuclear power plants. Whatever we're doing, let's do it. Most interstellar light sail concepts focus on unmanned spacecraft. With modern materials like carbon fiber sails driven by microwave beams from a single nuclear power plant, reaching 10% of light speed seems quite reasonable. This is a version of Robert Forward's Star-Wisp spacecraft, but scalable. If we want to carry real humans, we'd need a larger ship, meaning more powerful visible light lasers and larger sails coated with advanced reflective and heat-resistant materials like sapphire. This laser would have to be enormous, probably built on the moon and powered by massive helium-3 reactors or giant solar arrays orbiting the sun. How fast can this thing accelerate? Since we're not carrying fuel, the maximum speed depends only on the laser ACE power and alignment and the sail AS size. The longer the effective beam range, the higher the achievable speed. Achieving 10% of light speed or more is considered necessary. These technical challenges must be addressed in the weighting calculation. Slowing down on the other side is another major problem. There's the possibility of interacting with stellar winds from the target star, but it's complex. Ultimately, the scalability of light sails suggests that speeds above 0.1 C may be possible. Now we've saved the most impressive option for last, the black hole drive, technically a Schwarzschild Kugelblitz. This engine uses an artificial black hole to travel below light speed in one of the fastest possible ways. This black hole is made of light instead of mass. If enough laser energy is focused into a sufficiently small area, space-time can be curved into a singularity, creating what in German is called a Kugelblitz, meaning ball lightning. A properly sized black hole emits enormous amounts of Hawking radiation. The smaller the black hole, the more radiation it emits. And that radiation could propel our starship. The ideal case would be a black hole weighing about 600 billion kilograms, roughly the size of a proton. Such a black hole would emit about 160 petawatts of radiation, equal to 10,000 times Earth's energy consumption. And it would evaporate in about 3.5 years. Smaller, and it evaporates too quickly. Larger, and it emits weaker radiation and becomes too massive to accelerate efficiently. Assuming we could capture most of the radiation, this amount of energy could get us to 0.1 C in 20 days, and possibly to a significant fraction of light speed over the black hole's lifetime. It would undoubtedly be faster. Compared to other options, it's far superior. Also the most impressive among all sublight engines. Even the Romulans use it. The only downside is that the lasers required to create the black hole must be even more powerful than the black hole itself. It's possible, but still very far in the future. All right, there are many alternatives for reaching the stars. which is the fastest? Honestly, if we must colonize, nuclear weapons like in Project Orion are probably the best. The technology exists. We just need to increase our nuclear arsenal by 200 times, which isn't something we should do unless extinction is at stake. Still, in the most optimistic scenario, we might have a human presence in space by around 2120. Fusion engines are more sustainable, but at least 50 years away technologically. If we start immediately, we could reach Alpha Centauri in the second half of the 2100s. Pure antimatter and Kugelblitz engines are future starship technologies. Assuming faster-than-light travel doesn't work, we'll need such systems to explore the galaxy at near-light speeds and reduce perceived travel times to a human scale. Let's talk about near-future realities. I'll be clear, light sails. We will send our first unmanned probes to the Alpha Centauri system. After launch, it will take about 45 years. Then we'll need another 4.5 years to receive the message that we succeeded, since we 1T wait to slow down on the other side. Maybe within 30 years we could launch Starwisp, and some children watching this video might see it happen. Crude light sails are not that far off, and definitely possible. As humanity's first attempt to land on other worlds in space, we could sail toward the stars. It will probably lie somewhere between the fusion and post-fusion engines we discussed. In any case, it will be an incredible journey. Which option excites you the most? Share with us in the comments. In the next episode, we'll reach the 7th level of light speed in space-time. Last week, we discussed how the speed of light is actually the speed of causality. Many of you asked great questions. Andrea Propone and others asked why the speed of light has the specific value of 300,000 kilometers per second, and what would happen if it were different. Indeed, that number comes from somewhat arbitrary definitions of the kilometer and the second. Physicists usually prefer defining the speed of light as c/1, known as natural units. At this stage, it becomes more interesting to ask why the other fundamental constants of nature have the values they do relative to the speed of light. These ratios, the speed of light, the strength of fundamental forces, are important for the structure of our universe. Change them too much, and the familiar universe could not exist. We'll explore that and more in another episode. Jai Kolra and others ask what we think about quantum entanglement. Wouldn't that allow instant messaging? Right. As Einstein called it, spooky action at a distance seems surprising on the surface. When you collapse the wave function of one entangled particle, your measurement choices instantly affect the state of its entangled partner, possibly across vast distances. However, it turns out this cannot be used to transmit new information faster than light, so causality is preserved. We could do an episode on this, but in the meantime, you can watch a great explanation from Veritasium, linked in the description. Ed Stefan asks why we're suddenly talking about gravitational waves that were never seen before. We'll return to that next week. But for now, here is an interesting quote from Gareth Dean referring to their indirect detection. "We didn't see the duck, but something is quacking and eating all our breadsticks." Colonel asks, "Does this mean we could call the speed of light the total monkey speed?" And to Tyler Hamilton, I have only one thing to say: yes.